Welcome to the exciting world of AI system design. Today, artificial intelligence is no longer just a concept from science fiction. It is a powerful tool that is reshaping industries and our daily lives. From the recommendation engine that suggests your next movie to the virtual assistant that schedules your appointments, AI is all around us. But how do these intelligent systems come to life? The magic lies in AI system design. This discipline is the art and science of architecting robust, scalable, and reliable systems that are powered by machine learning models. It is a field that blends software engineering, data science, and domain expertise into a cohesive whole. Mastering AI system design is crucial for anyone looking to build impactful technology. It is not enough to simply train a high-performing model in a notebook. To create real value, you must know how to integrate that model into a larger application. You need to understand how to handle massive amounts of data efficiently. You must ensure your system can serve predictions quickly and reliably to thousands or even millions of users. This journey from a theoretical model to a production-ready service is what this guide is all about. It is a practical path for turning your AI ambitions into tangible, real-world solutions that work. This essay will guide you from the fundamental concepts to the advanced techniques needed to become a proficient AI system architect. We will start with the basics, exploring how AI systems differ from traditional software. Then we will walk through the entire life cycle of an AI project, from gathering data to deploying your model. You will learn the essential Python skills, dive into machine learning and deep learning, and understand how to build the data pipelines that feed your models. We will cover the critical steps of deploying, scaling, and maintaining your systems in a production environment. Our goal is to demystify the process and provide you with a clear roadmap. We will explore modern tools and best practices such as MLOps to ensure your systems are automated and maintainable. We will also touch on the important topics of ethics, fairness, and security in AI. By the end, you will have a comprehensive understanding of how to design and build complete production-grade AI systems. You will be equipped with the knowledge to tackle complex challenges and create the next generation of intelligent applications. Let's begin this incredible journey together. When we design traditional software systems, the logic is often explicit and rule-based. A programmer writes clear instructions that tell the computer exactly what to do. For example, if a user's age is over 18, grant them access. This logic is deterministic. Given the same input, the system will always produce the same output. The system's behavior is defined entirely by the code written by developers. The core challenge in traditional system design is managing complexity, ensuring scalability, and writing clean maintainable code that perfectly executes these predefined rules. The system's intelligence is a direct reflection of the developer's explicitly coded logic. AI-driven systems, however, operate on a fundamentally different principle. Instead of being explicitly programmed, they learn their logic from data. The core of an AI system is a model, not a set of hard-coded rules. This model discovers patterns, relationships, and features within vast data sets during a process called training. Its behavior is therefore probabilistic, not deterministic. For example, an AI model might predict that an email has a 98% probability of being spam. This introduces a level of uncertainty that traditional systems do not have. The system's intelligence is emergent, derived from the data it was trained on, rather than from explicit instructions. This distinction has profound implications for system design. In AI systems, data is as important as code, if not more so. We often say data is the new code. The design must therefore be data-centric. You need to build robust pipelines for collecting, cleaning, and transforming data. The system must also handle the inherent uncertainty of model predictions. This might involve setting confidence thresholds or designing fallback mechanisms for when the model is unsure. The system's behavior can also change over time as it is retrained on new data, a concept known as model drift, which requires continuous monitoring. Furthermore, the development lifecycle itself is different. Traditional software development is often linear, moving from requirements to design, implementation, and testing. AI system development, by contrast, is highly iterative and experimental. You might try several different models, tune numerous hyperparameters, and constantly go back to the data to improve performance. The system design must accommodate this experimental nature. It requires versioning not just for code, but also for data and models. This creates a new set of challenges and demands a new way of thinking about how we build and maintain software. Every successful AI system follows a well-defined life cycle, a journey that transforms raw data into a valuable, running service. This process begins with data, the lifeblood of any machine learning model. The first phase is data collection and processing. Here you identify the necessary data sources, which could be anything from user activity logs and databases to images and text files. Once collected, this raw data is often messy and incomplete. It must be cleaned, transformed, and prepared for the model. This step, often called data pre-processing or data wrangling, is one of the most time-consuming yet critical parts of the entire lifecycle. With prepared data in hand, we move to the modeling phase. This is where the learning in machine learning happens. You select an appropriate algorithm, be it a classic model like logistic regression or a complex deep neural network, and train it on your processed data. This involves feeding the data to the algorithm, allowing it to learn the underlying patterns. The process is iterative. You will likely train many versions of your model, adjusting its parameters or hyperparameter tuning and structure to find the one that performs best. Evaluating the model's performance using metrics like accuracy, precision, and recall on a separate test dataset is crucial to ensure it generalizes well to new, unseen data. Once you have a trained model that meets your performance criteria, the next stage is inference, which means using the model to make predictions on new data. This is where the model delivers its value. To do this, you need to deploy the model, making it accessible to other parts of your application or directly to end users. This could involve wrapping the model in a REST API, embedding it in a mobile app, or running it in a batch processing job. The key design consideration here is how to serve these predictions efficiently and reliably, whether in real time or in batches depending on the application's needs. The lifecycle does not end at deployment. A deployed AI system must be continuously monitored in the real world. The world changes, and so does the data. This can cause a model's performance to degrade over time, a phenomenon known as model drift. A feedback loop is essential to capture new data and monitor the model's predictions. This feedback allows you to detect performance degradation, identify biases, and collect new labeled data. This new data can then be used to retrain and improve the model, starting the lifecycle all over again. This continuous cycle of training, deploying, monitoring, and retraining is what keeps an AI system relevant and effective over time. Python has become the undisputed language of choice for AI and machine learning, and for good reason. Its simple, readable syntax makes it easy for beginners to learn, yet it is powerful enough for experts to build complex systems. Python's true strength in the AI domain, however, comes from its vast and mature ecosystem of libraries. Libraries like NumPy and Pandas provide a high-performance foundation for numerical computation and data manipulation. They allow you to work with large arrays and data frames efficiently, which is the bread and butter of any data-centric application. Mastering these tools is the first step toward becoming a proficient AI developer. Beyond data manipulation, structuring your code effectively is paramount for building maintainable AI systems. Object-oriented programming, or OOP, is a key paradigm here. By organizing your code into classes and objects, you can create modular and reusable components. For example, you might create a data preprocessor class to handle all your data cleaning logic, or a model server class to manage API requests for predictions. This approach makes your codebase easier to understand, test, and extend. As your AI projects grow in complexity, a well-structured object-oriented design will save you countless hours of debugging and refactoring, proving to be an invaluable skill. For the machine learning tasks themselves, Python offers incredible libraries like scikit-learn, TensorFlow, and PyTorch. Scikit-learn provides a simple and consistent interface for a wide range of traditional machine learning algorithms, making it perfect for getting started and building baseline models. When you need to tackle more complex problems with deep learning, TensorFlow and PyTorch are the industry standards. These frameworks give you the tools to build, train, and deploy sophisticated neural networks, from simple classifiers to massive language models. Familiarity with at least one of these deep learning frameworks is essential for any serious AI practitioner today. Finally, a professional AI engineer needs to think beyond just the model. Your Python code must be part of a larger, robust system. This means understanding how to write clean, documented, and testable code. It involves using version control systems like Git to track changes and collaborate with a team. You should also be comfortable with Python's packaging and dependency management tools, like pip and conda, to ensure your application's environment is reproducible. These software engineering best practices are not optional. They are fundamental to building AI systems that are reliable, scalable, and ready for the real world. So, at its core, machine learning is about teaching computers to learn from experience without being explicitly programmed. There are, two main types of learning. The first is supervised learning, where the machine learns from data that is already labeled with the correct answers. Imagine showing a computer thousands of pictures of cats and dogs, each one labeled as cat or dog. The model's job is to learn the mapping from the input, which is the image, to the output, which is the label. This is, honestly, the most common type of machine learning, used for tasks like classification, like, is this email spam or not, and regression, such as, what will be the price of this house? The second type is unsupervised learning, where the model works with unlabeled data. The goal here is to find hidden patterns or intrinsic structures within the data itself. For example, you might use unsupervised learning to group customers into different segments based on their purchasing behavior without knowing those segments in advance. This is called clustering. Another common unsupervised task is dimensionality reduction, where you simplify a complex dataset by reducing the number of variables while still preserving important information. Unsupervised learning is, honestly, incredibly powerful for exploring data and discovering insights you did not even know to look for. Before a model can learn from data, the data has to be in the right format. This is where feature engineering comes in. A feature is just an individual measurable property or characteristic of a phenomenon being observed. Feature engineering is really the art of selecting, transforming, and creating the most effective features from raw data to improve model performance. For example, from a simple date, you could create features like day of the week or month, which might actually be more predictive. Good feature engineering often requires domain knowledge, and, honestly, it's one of the most creative and impactful parts of the machine learning process. Once you have your features and your model, you need to evaluate its performance. It's not enough for a model to do well on the data it was trained on. It has to generalize to new, unseen data. To measure this, we split our data into training, validation, and test sets. We train the model on the training set, tune its hyperparameters on the validation set, and finally evaluate its real-world performance on the test set. We use various metrics like accuracy, F1 score, or mean squared error to, quantify how well the model is doing. This rigorous evaluation process ensures we deploy a model that is truly effective and not just memorizing the training data. AI systems are fundamentally data-driven, and their performance is directly tied to the quality and availability of the data they consume. Therefore, designing a robust data system is a cornerstone of building successful AI applications. This involves creating data pipelines, which are automated workflows that move data from its source to where it is needed, such as a machine learning model. A typical pipeline might extract data from a production database, transform it by cleaning and creating features, and then load it into a data warehouse or a feature store where models can access it. Building these pipelines ensures that data is fresh, consistent, and ready for training or inference. Data can be processed in two primary ways: in batches or in streams. Batch processing involves collecting and processing data in large groups or batches on a fixed schedule. For example, a pipeline might run once a day to retrain a model on the previous day's data. This approach is efficient for large volumes of data and is suitable for applications that do not require immediate updates, like a weekly sales forecast model. Tools like Apache Spark and workflow orchestrators, such as Apache Airflow, are commonly used to build and manage these powerful batch data pipelines, providing reliability and scalability for heavy-duty data processing tasks. In contrast, stream processing handles data in real time, event by event, as it is generated. This is essential for AI systems that need to react instantly, such as fraud detection systems that must block a transaction the moment it occurs, or real-time recommendation engines that update based on a user's latest click. Streaming data systems are built using technologies like Apache Kafka for ingesting high-throughput data streams and frameworks like Apache Flink or Spark Streaming for processing them on the fly. Designing a streaming system is more complex as it requires careful management of state and handling of out-of-order events. Ultimately, the choice between batch and streaming depends on the specific needs of your AI application. Many modern systems use a hybrid approach, often called a lambda or kappa architecture. They might use a streaming pipeline for real-time predictions, while also running a batch pipeline to perform more complex calculations or model retraining on a larger historical dataset. Building these data systems requires a deep understanding of data modeling, storage technologies, like data lakes and warehouses, and the trade-offs between latency, cost, and complexity. A well-designed data system is the solid foundation upon which every great AI application is built. Training a machine learning model is only half the battle. The real value is unlocked when you deploy it and serve predictions to users. Deployment is the process of taking your trained model and making it available in a production environment. One of the most common ways to do this is by wrapping the model in a web service with a REST API. This allows other applications to request predictions from your model over the network using standard HTTP requests. Python frameworks like Flask or FastAPI are excellent for this purpose. FastAPI in particular has become very popular for its high performance and automatic API documentation. When deploying a model, you must decide between real-time inference and batch inference. Real-time, or online, inference is used when you need immediate predictions. For example, when a user types a search query, a model provides suggestions instantly. This requires a constantly running server that can respond to requests with very low latency. On the other hand, batch inference involves making predictions on a large collection of observations all at once. For instance, you could run a nightly job to score all your customers for their likelihood to churn. Batch inference is often more computationally efficient but does not provide immediate results. As your application grows, a single server will not be enough to handle the traffic. You need to design your system to scale. This is where load balancing comes in. A load balancer is a service that distributes incoming requests across multiple instances of your model server. This not only improves performance, but also increases reliability. If one server fails, the load balancer can redirect traffic to the healthy ones. To handle fluctuating demand, you can use auto-scaling. This automatically adds or removes server instances based on the current load, ensuring you have enough capacity during peak times while saving costs during quiet periods. Optimizing for performance and cost is a continuous balancing act. Caching is a powerful technique to reduce latency and server load. If multiple users make the same prediction request, you can store the result in a fast cache, like Redis, and serve it directly without running the model again. Hardware choice is another key factor. Using GPUs or graphics processing units can dramatically speed up inference for deep learning models, but they are more expensive than CPUs. As an AI system architect, you must constantly analyze these trade-offs to build a system that is fast, reliable, and cost-effective, delivering the best possible experience to your users. As AI systems become more complex and integral to business operations, we need a disciplined approach to manage their life cycle. This is where MLOps, or machine learning operations, comes in. MLOps applies DevOps principles to machine learning workflows, aiming to automate and streamline the process of building, testing, and deploying models. A key component of MLOps is establishing a CI/CD, continuous integration and continuous deployment, pipeline. This automates the process of testing new code, retraining models with new data, and deploying them to production safely and efficiently. This automation reduces manual errors and accelerates the delivery of new AI features. A robust MLOps practice also involves rigorous versioning and monitoring. It is not enough to just version your code. You must also version your datasets and your trained models. This allows you to reproduce any experiment or deployed model perfectly, which is crucial for debugging and regulatory compliance. Once a model is deployed, continuous monitoring is essential. You need to track not only system metrics like latency and error rates, but also model-specific metrics like prediction accuracy and data drift. Dashboards and alerting systems can notify you immediately if a model's performance starts to degrade, allowing you to intervene before it impacts users. Beyond the technical aspects, building responsible AI systems requires a strong focus on security and ethics. AI systems can be vulnerable to new types of attacks, such as adversarial attacks, where malicious actors make tiny, imperceptible changes to an input to fool the model into making a wrong prediction. Securing your AI system involves protecting your data, your models, and your serving infrastructure from unauthorized access and manipulation. This includes implementing robust access controls, encrypting sensitive data, and regularly auditing your system for vulnerabilities to build trust with your users. Finally, we must address the ethical dimensions of AI, including fairness, bias, and explainability. Models trained on biased data will produce biased outcomes, potentially perpetuating and even amplifying societal inequalities. It is our responsibility as builders to audit our data and models for bias and take steps to mitigate it. Furthermore, many complex models, like deep neural networks, act as black boxes, making it hard to understand why they make a particular decision. The field of explainable AI, or XAI, develops techniques to make these models more transparent. Ensuring fairness and providing explanations for AI-driven decisions is not just good practice, it is essential for building trust and accountability. The recent explosion of generative AI has opened up a new frontier in AI system design. Models like large language models and diffusion models can generate stunningly realistic text, images, and code. Building systems with these models introduces a unique set of challenges and opportunities. One of the most fundamental skills is prompt engineering, which is the art of crafting effective prompts to guide the generative model toward producing the desired output. A well-designed prompt can dramatically improve the quality, relevance, and safety of the generated content, turning a general-purpose model into a specialized tool for a specific task. However, large language models have limitations. They can hallucinate or invent facts, and their knowledge is frozen at the time they were trained. To build more powerful and trustworthy generative AI applications, we often use a technique called Retrieval Augmented Generation, or RAG. A RAG system connects the large language model to an external knowledge base, like a company's internal documents or a real-time news feed. When a user asks a question, the system first retrieves relevant information from this knowledge base, and then provides it to the model as context along with the prompt. This allows the model to generate answers based on current, factual, and proprietary data, greatly enhancing its accuracy and usefulness. These building blocks, prompt engineering and RAG, are the foundation for creating sophisticated generative AI applications like advanced chatbots and virtual assistants. A modern chatbot architecture might involve a RAG system to provide factual answers, conversation memory to maintain context over multiple turns, and safety filters to prevent harmful outputs. Designing such a system requires orchestrating these components carefully to create a seamless and helpful user experience. The goal is to build an agent that is not only intelligent, but also reliable, safe, and aligned with the user's intent. By mastering these concepts, you gain the skills to build the next wave of intelligent applications. The journey through AI system design, from understanding the basics to deploying and scaling complex models, culminates here. Imagine building a capstone project, a customer service chatbot for an e-commerce site. You would design the data pipeline for product information using RAG, engineer prompts for different user intents, build a scalable API with FastAPI, implement MLOps for continuous updates, and ensure the chatbot is fair and helpful. This project encapsulates all the skills covered, from data engineering and machine learning to deployment and ethics, preparing you to solve real-world problems and innovate in this exciting field.